And so today, I'm Seref, by the way, and I'm a third-year PhD student at Yale, working with Nicolò Cesana-Arlotti, and he told me he is very unhappy to not being here today. And today I'll present my research with him on 12-month-old's categorization of events as likely and unlikely, but not necessary and possible. So throughout the first years of life, even before they start school, children learn a vast amount of information from their environment. So for example, they start to learn how to interact with their environment, they learn language, they learn abstract concepts such as numbers, but how come children learn all of these in a very short amount of time? And we know that one powerful mechanism is based on infants' ability to learn from failed expectations. So for example, they expect objects to stop when colliding with a solid wall, but when they see otherwise, they are surprised and learn from, this led them to explore and learn from these objects. But here, babies' expectations are based on facts or their core knowledge, and these facts are deterministic. So they know objects can't pass through these solid walls, and it is not possible. But not everything we learn from our environment is deterministic. In fact, most things are uncertain, and events can unfold in very different ways. So we usually don't know which possible state of the world is going to be actual. And this may sound too abstract to you, but this is what we experience in our daily lives. So let me show you an example. So when we hear this syllable, even before hearing the following syllable, we would expect to hear the word baby if we are talking with a new parent. But we would expect to hear the word bagel if we are discussing breakfast options. So how come babies form such expectations under uncertainty? And we know that infants are very good statistical learners, so they can track the regularities to form expectations of the possible state of the world. For example, infants can track transitional probabilities between syllables in a continuous speech stream to predict what units can be words. But here, to form an expectation, babies need prior frequency information. But what if they don't have this prior frequency information to build on? What would they do? And another line of studies examined this pure reasoning under model uncertainty in the lack of any previous frequency information. And here, babies are expected to use logical possibilities to guide their reasoning. And let me show you an example how this was studied in babies. And in this series of studies, 12-month-old infants were presented with a lottery box with 3 yellow and 1 blue objects. At the end of each event, 1 object exited the box, and these were one-shot events. Babies had no prior knowledge on which object exited the box more frequently. And in one condition, the blue object exited the box, which was an improbable outcome, but in the other, the yellow object exited the box, which was a probable outcome. And they found that infants look longer at the improbable outcome than the probable one, suggesting that babies can understand the probability of each outcome. But does this really mean that they can represent uncertainty using probabilities? So there are other interpretations of those results that do not require infants to understand probabilities, and here is why. And for example, in a lottery machine like this, we would have 2 possible outcomes, yellow and blue. And if children randomly pick one of the objects and expect them to exit the box, more children would expect the yellow one to exit, as there are more yellow objects inside the box. And when the outcome is the blue one, more kids would be surprised, thus look longer. And when the outcome is the yellow one, and less kids would be surprised and look longer, which would yield the same looking pattern that was found before, suggesting that infants might not understand probabilities at all. And so far, there is no clear answer in terms of whether babies do such pure reasoning under model uncertainty. And building on these ideas, in our study, we ask whether infants can represent uncertainty in physical probabilistic events for which they have no previous frequency information. And to answer this question, we ran 5 pre-registered online experiments with 12-month-olds. And in our first experiment, we presented infants with physical probabilistic events, which are lottery events, that were either likely or unlikely. So let me show you the movies. So in this movie, you can see that only 3 objects can exit the box, and 2 of them were blue cube. Then 1 blue cube exits the box, which had a 66% probability. So this blue cube is a likely outcome. And In this movie, on the other hand, only 3 objects can exit the box again, but this time only one of them was a blue cube. It exited the box, but this time it makes a 33% probability, so it's an unlikely outcome. And here you can see how we conduct the experiments. So babies first watch the objects bouncing inside the box, and the moment the outcome objects started to exit, we coded their looking times, and whenever they start to look away from the screen, we stop coding. And if babies stop looking for more than 2 seconds, then we end the trial. And our experiment consisted of 3 phases: first baseline, then habituation, and finally test. And in the 4 baseline trials, infants were presented with likely and unlikely events, alternated in different trials, and we measured how long they looked at each event. Next, we had the habituation phase. Here, infants were repeatedly presented with variations of likely 66% events, every time with new types of objects. But each outcome event had 66% probability. And after the habituation, infants were presented again with the same likely and unlikely events they saw in the baseline, and we measured their looking time again. And from these looking time measures, we calculated the percentage looking times at unlikely 33% outcomes using this formula, both before and after the habituation. And then we compared these 2 measures. And if they somehow understand the model uncertainty, we predicted that their percentage looking at the novel unlikely 33% events should increase after habituation to likely 66% events. All right, so here on the y-axis, I'll plot babies' percentage looking times at unlikely events. Thus, higher values would indicate a preference towards unlikely events. Remember, if children understand model uncertainty, we expected an increase, but if they don't, we expect it to stay the same. All right, so now let's see the results. Okay, so as you can see, we found an increase in the percentage looking times at unlikely 33% events after being habituated to likely 66% events, suggesting that babies can represent model uncertainty. But if babies can really understand model uncertainty here, then they should be able to discriminate these likely and unlikely events, not only when habituated to likely events, as we did in first experiment, but also when they are habituated to unlikely events. And this is exactly what we did in our second experiment. And here we presented unlikely 33 and likely 66% events in the baseline and test, but this time infants were habituated to unlikely events. And this time we calculated the percentage looking time at likely 66% events and compared this measure across baseline and test. And here, if they represent model uncertainty, again, we should expect an increase. And here on the left, you can see the results of the previous experiment. And here you will see, you saw unlikely 33% outcomes. But on the right, differently, I'll plot percentage looking times at likely outcomes before and after habituation to unlikely events. So here, higher values would indicate a preference towards likely events. And here are the results. So in this experiment as well, we found that infants' percentage looking times increased after being habituated to unlikely events. So it seems like babies' responses are shaped by what they are habituated to, as predicted by the model uncertainty account. All right, so with these 2 experiments, we answered our first question. So our findings revealed that infants can discriminate likely and unlikely events, suggesting that they might be able to somehow represent model uncertainty. But there remains an important question. We still don't know how they represent it. So let me quickly unpack what I mean by this question. So when babies are watching these objects bouncing inside the box, one possibility is that they represent the probabilities. For example, infants may infer the ratio of blue cubes and red balls, and then use these ratios to continuously represent uncertainty with probability values. Or they may use model categories, such as thinking which toy is likely or unlikely to exit the box. So to do that, they represent all possible outcomes and then quantify over these representations to decide what is likely and unlikely. And currently, both types of representations can explain our results for the first 2 experiments. But we don't know which one babies used in our task. So to answer this question, we ran our third experiment. And in this experiment, we changed the baseline and test events. Here, we presented infants with likely 66 and necessary 100% events. And in the necessary 100% events, as you can see, the only possible outcome is the blue one. And during the habituation, baby sees likely 66% events every time with new objects. And from here, we calculated the percentage looking times at necessary 100% outcomes. So we expected that if children can represent probabilities, their percentage looking at the necessary 100% events should increase from baseline to test, as this is a novel probability level. But if they represent them with model categories, their relative looking should stay the same. So this is because both events are, by definition, likely, meaning that both events have higher chances of happening than not happening. Okay, so now let's see the results. So you can see that we found no change in their percentage looking times at necessary events. So this means children did not distinguish between necessary and likely events, which was expected by the model categories of likely and unlikely. But before drawing any conclusion, we need to address a confound. So it is possible that babies did not understand the barrier's function in our stimulus. So if this is the case, when you imagine these boxes without the barrier, both boxes are the same. So the outcome blue cube would have 75% chance of exiting the box in both conditions. And to control for this barrier effect, we ran our fourth experiment. And in the stimulus, we only removed the barrier and the object above it. Other than that, the experiment is identical to the previous one. All right, so here is our results. In experiment 4, they still did not distinguish between 100% and 66% probability events, even when there is no barrier in the stimulus. So this suggests that the lack of discrimination between these probabilities in the previous experiment was not due to the low-level confounds, but it could be that babies might lump these two probabilities under the same category, which could be likely. And with these two experiments, we also answered our second question. So infants can represent uncertainty with model concepts such as likely and unlikely, as we found that infants did not discriminate between probability levels such as 66% and 100%. But there is also another alternative explanation that we need to deal with. So in our studies, we repeatedly presented likely 66% events during the habituation phase. Thus, every time we present a likely event, regardless of the object identities in the lottery box, infants always saw the object of the majority kind as the outcome. So one may think that babies learn this rule across the habituation trials, so which would also account for the same pattern we observed in our data. And to address this concern, we revised our lottery movies. So we edited our stimuli so that outcome tube is not attached to the box. This means the outcome tube only reveals an object that was already hidden inside from the beginning. So probability is not relevant in this situation, but still the outcome object is one of the majority kind in the box. Therefore, the same statistical rule applies here as well. And here the procedure is again similar to the previous studies. In the baseline and test, babies see minority versus majority outcome trials, and they were habituated to majority outcomes. And if babies were sensitive only to this majority rule, then their percentage looking times at minority outcomes should increase after the habituation. And just to note that we are still collecting data for this experiment to reach for the pre-registered sample size, so please take these results with a grain of salt. And here are the results. So for now, there is a slight trend, but this trend is not significant, and the base factor is slightly favoring the null hypothesis, but it's not conclusive, showing that in the previous experiments, babies possibly did not use this just tracking statistical regularities. So they don't really, they probably used unlikely, likely distinctions compared to this majority rule. And in conclusion, in the present study, we investigated whether and how infants represent model uncertainty in physical probabilistic events. And in experiments 1 and 2, we found that babies distinguished between model uncertainty levels, namely likely 66 and unlikely 33% events. And further, in experiments 3 and 4, we found that infants did not differentiate likely 66 and necessary 100% events. So infants might lump these two probabilities under the same category, which could be called likely, suggesting that infants represent model uncertainty with model categories. And finally, in experiment 5, we showed that this was not due to a superficial statistical regularity learning, but rather it is sensitive to the context of model uncertainty. And all of these suggest that infants as young as 12-month-olds can represent uncertain events as likely and unlikely. And these findings would add to the literature that learning under uncertainty is not just limited to the tracking statistical regularities in the past experiences. Rather, there is a genuine pure reasoning in the absence of any frequency information, which are guided by logical or model categorical representations, such as likely and unlikely, instead of continuous probability values. And in conclusion, these findings open an exciting possibility that logical representation can give rise to infants' reasoning and learning. And thank you so much for listening, and thanks all of the RAs and lab managers who worked in this project.